Ladies and gentlemen, we have completed section 1 of chapter 1 in linear algebra, elementary linear algebra by Anton and Call. We just have one more question to check today, and then we'll be into the next section. So let's pull up Quizlet and check my answer on number 26. Systems, here we are. Let me grab that. What's going on? All right. Would we have got this correct or not? Here we are, a plus b, okay. Got this. Got that part right. We would expect the system to have exactly one solution. Expect the system to have one solution. We expect it to happen because the points are non-collinear and x coordinates are all distinct. Non-collinear. I would expect the system to have one solution because it doesn't appear to have infinitely many solutions because the equation aren't simply multiples of each other. I think that might be what collinear means. Yeah, sounds about right. There you have it. You've just seen us complete 1.1. We have left problems to interleave in the future. But now it's time to get into 1.2 Gaussian elimination. So I'm going to begin reading and then I'll be back to recall. And I've got some info on this set. All right, so I just read the intro paragraph as well as a paragraph on a section called considerations when solving linear systems. So basically this section, section 1.2 is about solving linear systems via elementary row or row operations on augmented matrices. And considerations, this section called considerations when solving linear systems, or about solving linear systems, is basically grouping in two different types of linear systems, small and large. Large are like enormous. So we're talking like you cannot solve by hand, like up to millions or more of unknowns, or not even necessarily that much, but that's how big they can get. With those, or with small, you can solve by hand. With large, you're going to use a computer. Other things come about, such as memory size, solving time, round off error. But they're basically, solving large linear systems is based off of solving small linear systems, but you use a computer, and you got these other aspects, and these other aspects in solving large linear systems that's addressed and studied in the field of math called numerical analysis. We just started talking about echelon form, and this is basically, it seems to be echelon form of a matrix is basically where it shows you the solutions of the linear system, or it can be interpreted that way. So yeah, solving large linear systems is only touched on in this book, not really delving too deeply. So now we're going to read about echelon forms and what makes an echelon form. So I'll be back in a little bit. All right, so echelon forms, we learned about two echelon forms, reduced row echelon form and row echelon form. Okay, row echelon form is the bigger set. Reduced row echelon form is within row echelon form. So all reduced row echelon form is in the form of reduced row form, row echelon form, but not, one more time. All reduced row echelon forms are also row echelon forms, but not all row echelon forms are reduced row echelon forms. Okay, well, what makes something a reduced row echelon form? What makes a matrix? When do we say it's in reduced row echelon form? There's 4 criteria. First, for every row, if it's not all zeros in the row, the first digit from reading left to right is a 1. We call that a leading 1. If the row is all zeros, it's at the bottom of the matrix. Okay? For reduced row echelon form, another thing, those are two of the four. Another thing is that reduced row echelon form, if there's a column that has a leading 1, there's no other digits besides 0 in the slots above and below that leading 1. And then what would be the fourth thing? Or is that everything? Got the zeros at the bottom, first digit. Oh, right. For two rows that are consecutive that have leading 1s in them, the one on top, the leading one is more to the left, and the one below it, the leading one is more to the right. Okay, that's how you know. That's the criteria for a matrix to be in reduced row echelon form. What is reduced? No. What is just row echelon form? It's the same thing except for that above and below a column that has a leading 1 has no other digits besides 0. For row echelon form, it can have digits that are non-zero in the column. That's row echelon form. If there's no digits besides 0 above or below the leading 1s in a matrix, then it's in reduced row echelon form. If there is digits besides 0, then it's in row echelon form, not reduced row echelon form. Okay. Looking at it further though, based on how the leading 1 has to be the leftmost if it's above, well, for reduced or for row echelon form, there's only going to be non-zero digits above the leading 1s potentially, not below. And for reduced row echelon form, it's gonna have zeros above and below. Row echelon form, zeros below only the leading 1s in the column. Reduced row, zeros above and below leading 1s. Got them? Got everything? I believe so. Yep. All right, now I'm gonna keep reading. I've got a few more minutes. I can get through more, so I'll be back in a little bit. All right, guys, wrapping up for today. I just learned that if we can get an augmented matrix into reduced row echelon form, then we can solve the linear system via either inspection, just by looking at it, or two, by parametric equations. Okay. And then we looked at leading and versus free variables. Leading variables are variables in a linear system that correspond with the leading 1s in an augmented matrix. Free variables are variables in an augmented matrix that do not correspond with leading 1s, right? I think that maybe when you have free variables, you're going to solve potentially via parametric equations, but we haven't got that far. If the bottom row is all zeros, or you have rows at the bottom of the matrix that are all zeros, cool, you can ignore them. If you have rows that are all zeros except for the last digits of 1, no solution, because then you have basically 0x, 0y, ... 0, whatever, xn equals 0, which 0 it's not equal, or equals 1, which 0 does not equal 1, no solution. Inconsistent linear system. So that's it for today. Feels great to make progress. We started reading Gaussian elimination 1.2 today. We got through 2.5 pages of reading. So that's good pace for reading. Really good pace, yeah. Considering it's like day 20 potentially, and we're on page 13. We did read 2 appendices, so that's it for today. I'll talk to you guys later. See ya.